Welcome to this explainer, developers. Let's talk about fixing your AI's amnesia and making absolutely sure it never loses context again. Because if you've ever built a conversational agent, you definitely know the pain of watching it drop the ball and act like it just met the user 3 seconds ago.
We've all been there, right? You're diving into the problem, trying to figure out why your customer service bot suddenly suffers from amnesia mid-conversation, completely losing track of vital instructions. You've coded the logic, you've hooked up the API, but out of nowhere, the AI acts like the last 3 messages never even happened. It's incredibly frustrating for you as a developer, and honestly, it's a total deal breaker for your users.
So here is our roadmap to fixing this. We're going to cover 1. The AI amnesia problem, 2. The RAM versus storage analogy, 3. Building the buffer class, 4. Sliding window versus tokens, and 5. Some advanced memory techniques. Let's jump right in. Section 1. The AI amnesia problem and preserving that crucial conversational flow.
Imagine this kind of multi-turn financial conversation. In step 1, a user sets a buy target, saying buy CE above 24,000. The assistant acknowledges it. Then the user sets a condition, keep SL 50, a stop loss. Finally, the user asks, what is my plan? Now, if your AI operates without a built-in memory buffer, it has absolutely no idea what was just said. It looks at that final question in a total vacuum and is just going to give a blank or super confused response.
So the fix here is a conversation buffer. This basically acts as a rolling chat history that the large language model always checks before answering. It's a highly specific implementation of short-term memory. It captures those recent user inputs and assistant responses in strict chronological order, ensuring that each new message builds organically on the previous ones.
Moving on to Section 2, the RAM versus storage analogy for managing AI memory layers. To really wrap our heads around this, think of the conversation buffer as your computer's system RAM, governing the active chat window. It's fast, it handles exactly what's happening right now, and it's absolutely essential for immediate continuity. On the flip side, your vector database acts as the long-term system storage. It's your hard drive. That's where you store massive amounts of past data, but you obviously wouldn't load your entire hard drive into RAM just to answer a quick follow-up question. This hardware analogy brilliantly illustrates why the short-term buffer has to be the very first context layer accessed in your system pipeline. When user input comes in, it immediately hits the conversation buffer to grab that immediate context. Then, and only if needed, it queries the vector memory retriever for deeper, long-term context before finally sending the whole package to the LLM for a cohesive answer.
All right, Section 3, building the buffer class under the hood in Python.
We see a lot of broken code out there when developers first try this. Using a raw append method where you just keep tossing messages into a list? Absolute disaster, because your memory is just going to grow infinitely. If you mix your short-term buffer with your full conversational history, it gets way too bloated. And honestly, the most dangerous flaw is just appending raw text without defined message roles. You are going to severely confuse the LLM doing that.
To fix that, your conversation buffer class needs a really rigid structure. It must clearly separate the user role from the assistant role. By structuring your memory as a list of dictionaries with clearly defined roles and content, the AI can properly interpret the exchange. It knows exactly what it previously said versus what the user just commanded. So a correct Python design initializes the conversation buffer class with a predefined limit, like setting a window size to 5. Implementing a fixed window size automatically drops old messages and keeps your context lightweight and efficient. This ensures your system doesn't bog down and crash as the chat stretches into dozens of turns. Which brings us to Section 4, sliding window versus tokens, and how to optimize those constraints. Let's look at how the traditional sliding window behaves. It physically rolls forward over time. Imagine your buffer is currently holding messages 1 through 5. The absolute second that message 6 arrives, message 1 is instantly dropped to maintain that strict 5-message limit. It's a straightforward first-in, first-out protocol that guarantees you're always keeping the most recent context.
Now, while sliding windows based on message counts are incredibly easy to code, comparing them against token-based constraints proves that counting tokens is far, far superior. Why? Well, 5 short messages like yes or no take up barely any memory. But 5 massive paragraphs, that risks a catastrophic token overflow which leads to your system crashing or throwing nasty errors.
Setting a strict maximum token limit, like a max tokens variable set to 2,000, aligns perfectly with the LLM's actual capacity, instead of just blindly guessing with message counts. By optimizing for tokens rather than an arbitrary number of messages, you ensure fast, crash-free responses every single time.
Section 5. Advanced Memory Techniques. These are your pro developer tactics.
To really master your customer service tool, you can't just rely on basic dropping. You need to utilize pro techniques, summarizing old messages before they fall out of the window, pinning high-priority instructions so they stay active, and leveraging hybrid retrieval with a vector database to blend that short-term RAM with your long-term storage.
Take summarization as an example. Instead of deleting old messages entirely when your buffer gets full, you can pass them to a background process and summarize them into a single dense sentence. For instance, a long, rambling chain of trading questions gets condensed down to simply, user is following breakout strategy. Now the bot retains the broader context without eating up all its active RAM.
You can also use pinning logic to lock in priority instructions. Imagine writing a quick conditional check in your code. If the word strategy is in the message, pin that message. This ensures that crucial constraints, like that stop loss of 50 we talked about earlier, never slide out of the active window, no matter how long the casual conversation goes on.
So as a final checklist for your build, follow these best practices. Always keep your buffer relatively small, somewhere between 5 and 20 messages. Strictly enforce that user and assistant role-based structure we discussed. Optimize for tokens, not just message counts, to avoid bloated responses. And finally, combine this short-term buffer with long-term vector retrieval, often called RAG, for the ultimate bulletproof memory system.
At the end of the day, if you take away nothing else from this explainer, remember this one insight. The conversation buffer is simply the AI's grasp of what just happened. It's the absolute core mechanism that makes chatting with an AI feel natural, continuous, and highly contextually aware.
So I'm going to leave you with this final thought to explore in your own tools. When you sit down to architect your next customer service bot, are you risking an overflow crash by lazily counting messages? Or are you safely optimizing for tokens to build an unbreakable system? Thanks for tuning into this explainer, and happy coding.